So I think everybody has heard about climate change. If you are here, you are probably interested in the problem and probably worried about it. So you have probably also heard about various solutions being proposed and temperature targets being put up, like 2 degrees centigrade global warming or 1.5 degrees centigrade global warming and so on. There are many issues in defining these and in trying to meet these kind of targets. The first thing is when you say global warming of 1.5 or 2 degrees, it doesn't say anything about what it will mean for warming over India. For example, the top plot shows that 1.5 degrees warming with a cumulative risk over India will be much higher. Somebody, Tejanda, I'll come to you in a minute. So the number of extreme rainfall events or heat waves or sea level rise at a local scale will not be necessarily well defined by a global target. So the global targets are good political definitions. Stern and Nordhaus, as an economist, started this idea of looking at global mean temperature targets to try to translate them into actions needed, which seems like a very handy, tractable target, but actually they are a nightmare. It's not so easy to convert them into local action, which will add up to global solution or local impacts of a global target. Tejanda, what was the question?
Yeah. So,
hello? Yeah.
Yeah. So my question is like how we can quantify the impact of deforestation on means like a particular region is something in particular region is there if there is a natural sanctuary and if we want to in a particular district or maybe in the state level if we are doing any analysis, how we can quantify the impact of as you mentioned in your talk that a local as well as global. So what are the different models available to address such issues?
Yes, okay, good question. So from a theoretical point of view, we know many things. For example, trees have what is called evapotranspiration. So they are taking up water from the roots, taking up to the leaves. The stomata have to open, capture the carbon dioxide without losing too much water. So we know, for example, that increasing carbon dioxide increases the so-called stomatal conductance, which means the amount of time the stomata has to remain open doesn't have to be very long because the CO2 is high, which means they don't lose as much water, so they reject that water back into the ground. So in fact, you change the soil moisture and the river runoff and so on. And there are experiments done on a larger scale, like in the West African monsoon experiment, where a barren land was taken and was forested, and the idea was to see at what scale a local forest begins to affect the local microclimate. So such knowledge exists, but on a large scale, what we try to do is essentially rely on models. So models which have reliable skill in reproducing global circulation, global rainfall patterns, global temperature, etc., with vegetation. In the model, you can take out the vegetation or reduce its density or whatever else and see how that affects local climate and global climate. So this is typically how the so-called attribution experiments are done. So you have detected a signal, and if you want to do attribution to forest, you can remove the forest and put it back in, or urbanization and so on. So there are some uncertainties, but the confidence is enough to say how forests can affect local and global climates. It comes down to scales. How large the deforestation has to be. There are some very interesting results I can mention briefly in the Amazon. When they strip mined the forest for logging, for timber, the strips where the forest was deforested changed the albedo or the reflectivity in such a way that it warmed up faster. So it started taking moisture from the forested areas and increased the rainfall over the deforested area. So this depends on the scale. There are many such details. So essentially, we tend to rely heavily on models for larger scale attribution experiments of various things. Okay. All right. So what are the other targets? So the temperature target, as I said, is political, not very solid in my opinion, but nonetheless, it is going to be carried along. The other one is, of course, decarbonizing. So we know that carbon is the main culprit here, and we know how much we are emitting. So here is some historical period from 1980 to 2015. We are near 40 gigatons of carbon per year globally. And depending on the temperature you want to aim for, you want to reduce the carbon in the atmosphere at a certain rate. But this depends a lot on future assumptions of what kind of technologies will come in, what kind of renewables will be deployed, whether we will have an ability to capture the carbon from the air and sequester it, whether we will have transportation sector changing dramatically to reduce emissions, whether energy section. So basically it comes down to reducing the energy intensity of lifestyles and GDPs per capita and national GDPs, and carbon intensity of energy production. So energy intensity of GDP and carbon intensity of energy. So there are lots of uncertainties in this as well, basically because we are in what is called a carbon trap. So even as an individual, if you try to track your carbon footprint, your food miles, your driving habits, and so on, it's not so easy for one person to manage the system. The system is bringing you blueberries from somewhere. You have no idea what kind of carbon footprint was involved in producing it or transporting it to you, and so on. So it's a very difficult problem. Nonetheless, this is one of the scenarios that the IPCC considers. What are the costs involved and what are the technologies required and what are the socio-technical transformations needed to shift the future of carbon emissions to reach our target. The best thing to remember is that this idea of reducing emissions is just a fantasy. I think only way to go for it is to completely decarbonize. Doesn't mean that we will not emit carbon. It means that we will be able to take out any carbon we emit. So we need to drive technologies. For example, if you have kids that are looking for good projects and PhD topics or technology, they want to be entrepreneurs and make a lot of money, then obviously it's going to be in reducing emissions or taking out carbon from food, agriculture, and so on, from water use, from energy production, from transportation, and so on and so forth. Okay, so
if I may ask a question, so there's no hope for carbon sinks, for restoring carbon sinks, restoring forests and cleaning up our oceans and maybe doing something to reduce the temperature in the oceans? There's no hope for that?
Right now, there is no scalable technology. If you look at the plastic recovery, for example, technologies are being tried to sweep up plastic, but microplastic has already hit the bottom and it's going to stay there for a while, hopefully just stay there like PCBs in the Hudson River. But the distributed carbon, see, the carbon capturing at source is not difficult, but it's not scalable, because the fact that carbon is such a small amount itself means to filter out carbon, you have to filter out a lot of the air, right? Just the volume of air you have to flow through the system to remove carbon is very high. So the cost of carbon in that sense, the cost you put on it has to be very high. It has to be like, let's say $600 per ton of carbon. Right now, carbon is trading at less than 100, maybe $10 per ton or something. So in other words, you need subsidies. You need to somehow fund carbon removal, either it's from the ocean or from whatever. So once you put it in the air, it becomes distributed in small amounts, then it becomes very difficult. So in that sense, reducing emissions itself at source becomes important, and taking it out becomes important. So both technologies are being pushed forward. Emissions from cars are being reduced. Of course, Trump wanted to cancel the emission standards and so on. I think he already did. But the auto industries have learned their lessons. In 2008, Japanese were zooming along because they had efficient engines and the US industry didn't. So the industry itself is catching on to many of these things. They realize that future needs green technologies to make money. So green markets themselves may pick up. So I'm not saying there is no hope. I'm saying we should be aware of the magnitude of the problem. Sometimes these kind of simplistic figures miss the scale needed to do these things. Okay?
Yes, so if we could just talk a little bit about how 1.5 degrees is likely to affect India and possibly Sri Lanka and the Indian subcontinent in general.
Yes, so first of all, India and Sri Lanka are already above 1.5 degrees warming. So in the sense that the warming will not be uniform. When you are increasing carbon dioxide in the atmosphere, it gets distributed evenly, but because of the weather and climate and because of local agriculture and forest and desert and so on, the warming will not be uniform. And because the ocean circulates, the sea level rise will also be not uniform. Okay, think of coffee sitting in a cup and put a stirrer inside and stir it, right? It will become, it will dip in the middle and rise at the end and so on. So on a rotating earth, everything gets distributed because of the dynamics of climate, ocean circulation and wind. So in that sense, tropics are warming already quite a bit. And I think I can pull out a figure, but Indian Ocean has warmed up quite a bit and India has warmed up quite a bit. So I think globally speaking, we are already past this, but the impact is mostly in terms of heat waves. The number of heat waves have increased and the magnitude of heat waves has increased. But what is more dangerous is because warm temperature holds much more humidity, and because India and Sri Lanka are surrounded by a warm Indian Ocean, the humidity increase at some point creates a huge problem because human body is able to sweat and get rid of the heat when the air is dry. But if the humidity in the air begins to increase, then you reach what is called wet bulb temperature, which the body's ability to cool by sweating begins to go down. So this is something we have to really watch out for. When are we going to hit that? That it turns out that a wet bulb temperature of 35 degrees will kill you, basically. So you have to keep an eye on where that is headed. Plus, the so-called extreme events have become more in number and they have become widespread, which means the heavy rain events of more than 150 millimeters per day are not only more, but they are now on the scale of 10,000 square kilometers. So they are not at local popcorns that it's raining only heavily in Mumbai. Like this is raining on large central India scale. So, and of course there is sea level rise at the coasts and that's related to mangrove losses and so on, other things. But so heavy rain and heat waves are already here. Diseases, of course, because warm temperatures favor microbes and rain spreads it. So India has, it's basically a petri dish where warm temperatures breed all kinds of diseases and monsoon just spreads it. So now we had a cyclone. We have to see what it did to COVID, and we are getting monsoon into the monsoon season soon. So we have to see what it will do, and so on. So all the bad news is already here.
The figure you show here, the population affected by various risks in millions of people. So the figure, I just to have some clarity on that, is 3,960 per million people, or?
Yeah, no, that is the millions of people. So look at the scale on the left here, risk score. So India has a very high risk score. Pakistan, India, Afghanistan, Nepal, Bangladesh, they have a very high risk. So this is the total global number of millions of people. So that is almost 3.9 billion people, water stress of 3.34 billion people, and risk of power reduction, power production, and so on. So those are millions of people. Okay.
Yes, we can move on.
Okay, so is everybody back?
Yes.
So I'll continue. So this is I already mentioned Earth system before. Basically, everybody has a sense of what a system is. You can think of human body itself as a system. We have digestive system, skeletal system, blood circulation system, endocrine system, and so on and so forth. And system is something basically that functions together when the components are working together to produce a result that is not produced by each component by itself. So the old joke is that what is the difference between a dead cat and a live cat? A live cat may be just breathing, maybe blind, deaf, paralyzed, or whatever, but as long as it's breathing, we call it live cat. But to be fully functional, it has to do various things, right? So Earth system in that sense has all these components of what we have been talking about, the physical climate, but it also has biogeochemical system at the bottom, which is all the chemistry in the air, in the water, on land. Ocean has all, nitrogen, oxygen, zinc, copper, phosphorus, everything. And there is atmospheric physics and dynamics. So that is the circulation, winds, humidity, clouds, and then there is ocean dynamics. Basically, there are energies and temperatures, humidities being exchanged between each of the boxes that we see here. The main idea to remember is on the left-hand side, we have what is called external forcing. So we have talked about sun's energy coming in and orbits changing. So that external forcing is the main thing that drives the Earth system. And we have also listed volcanoes because volcanoes are basically taking out the carbon dioxide, methane, sulfur, and so on that is buried inside and throwing it suddenly into the atmosphere. So they are also considered external forcing. So those two are on that side. On this side, humans have also started to become an external forcing now. So in this sense, the forcing has a very definite, exact definition. A forcing is anything that changes the energy balance. So you have incoming solar energy and outgoing long wave or infrared energy. Any activity that changes the balance is called forcing. So human activities by deforestation or by changing carbon dioxide, greenhouse gases, we are changing this energy balance. So that is the forcing. And these arrows back and forth basically show you various feedbacks. So if you just look at, for example, atmospheric physics dynamics and ocean dynamics box arrows going back and forth, if the atmosphere gets warmer, then ocean will evaporate more. Water vapor traps more heat. It's a greenhouse gas, which means temperature will go up. So ocean will evaporate more and so on. So there is a positive feedback between those two. And there are similarly feedbacks between various other boxes, which together determines Earth's climate. This figure, which probably should have been put earlier on, I already mentioned Earth is a rotating system. So since you are probably drinking coffee, you can think of this on the left side. If you take a cup of black coffee and put milk in it, it will slowly diffuse and it will look like on the left panel. But if you put a stirrer inside and swirl it, then you will get these kind of streaks in the milk and the coffee. And that is because of the rotation. So if you look at the Hubble telescope picture, for example, everything in the universe seems to have these kind of swirls because the whole universe is rotating and everything is rotating. So nebular dust, solar system, everything tends to get organized into planes. This makes a huge difference because it makes it harder to mix in the ocean and mix in the atmosphere and to move faster and so on and so forth. So again, I'm answering the questions in the sequence in which you had listed them. So the figures may look a bit out of place, but here is a figure of a cyclonic flow and the anticyclonic flow. Cyclonic comes from the Greek word, which means going in the same direction as the rotation of the Earth, which is like a hurricane or a cyclone. So there is a low pressure in the middle and higher pressures around it. And when you add Earth's rotation to it in the northern hemisphere, you know that hurricanes go in the counterclockwise direction. So that is a low pressure or a cyclonic flow in the left panel. Anticyclonic flow is where you have a high pressure and circulation is going in a clockwise direction. And you can relate it to earlier rising air, sinking air kind of calculation, where if you have a low pressure, that means air is converging into it and air has to rise. So in the cyclone or a hurricane, you have rising air in the middle, low pressure. Rising air expands, cools, creates rain. So cyclones and hurricanes carry a lot of rain. And anticyclone does the other way. So on a desert, you have high pressure, sinking air. So air is flowing away from the surface. Air is sinking from the top and so on and so forth. So if you look at this figure, I don't know if you can see something is unusual in it. I say, do you see something unusual? Essentially, the lines, the circles here shown are constant pressure lines. And if you look at the thick arrows that are being shown are flows around the pressure center. So flow is actually along constant pressure lines. If you look at pressure, if you look at the weather charts being shown on TV, you may not have noticed, but next time you can notice carefully. They will show pressure and winds, and you will see that winds are often flowing along constant pressure lines, which is not very intuitive because wind should go from high pressure to low pressure. But in a rotating system, you can balance the rotational effect with the pressure gradient force, and you can create flow along constant pressure lines. There are other details like friction and so on, but nonetheless, this is what gives us weather and climate, unusual circulations. That's what gives us winds. Winds can go around the globe, they can climb over the mountain and get to the other side, but oceans have boundaries. So if winds are dragging the ocean from east to west in the tropics, for example, in the Pacific Ocean, then you can see the currents are going, for example, what is called equatorial, south equatorial current and north equatorial current are going from east to west. They hit the boundary, then they go south and north, and then you create these swirls or gyres, and so on and so forth. So ocean has very detailed circulation, which determines how water flows and where temperature is warmer and where it's colder. If cold water is coming up from the below, then it will be cold. If surface water is sinking, then it will be warm, and so on and so forth. So ocean and atmosphere essentially talk to each other. And I think there was a question about how feedbacks work. This is an example of negative and positive feedbacks. So you can think in a simple way. Let's say you have an AC. You set the thermostat to a certain temperature, and the AC starts blowing if the temperature gets warmer, and it'll stop blowing if the temperature gets cool enough, right? So the thermostat here is controlling the feedback between the temperature and the flow of cold air. This is called a negative feedback, which means if temperature increases, AC will turn on. If temperature decreases, AC will turn off. So this is a stable system. So negative feedbacks give you a stable system, whereas positive feedbacks will give you a runaway warming or runaway cooling. So this looks complicated here, but let me use a simple example. Let's say you are thinking about glaciers and warming, okay? So let's say something happened. Let's go back in time and say before greenhouse gas effects, anthropogenic forcing, and so on. And let's say we were with the dinosaurs and there was no glacier anywhere. Somehow, energy decreased. So let's say Earth's orbit changed in such a way that the sun's energy distribution changed and began to cool the higher latitudes because less radiation was being received, let's say, in the northern hemisphere. So the cooling starts and glaciers begin to build. How do glaciers build? Basically, if you have warm temperatures in the tropics, you are still have rising air, moist air flowing towards the poles. They are bringing moisture towards the poles, but it's cold, so they start to snow. Snow falls on land. It's cold, so it doesn't melt from this winter and stays to the next winter. Then next winter, more snow falls on top, so it compresses and builds a glacier. So glacier begins to build. Now, the glacier has high albedo or high reflectivity, so it begins to reflect more of sun's energy and begins to cool the atmosphere even more. So you will begin to increase the snowfall and you will begin to build the glacier even more, and the glacier extent will begin to increase. So the glacier will begin to come towards lower latitudes. So this is called ice albedo feedback. This is a positive feedback because whatever started the cooling, let's say sun's radiation change because of orbit change, glacier begins to build, glacier increases the albedo, glacier cools the temperature further, causes more snowfall, and glacier grows more in extent, albedo increases further, and cooling happens further. So you keep on building the glacier till something breaks this cycle and glacier begins to melt. That's a positive feedback. What is happening now? You still have a ice albedo feedback, but you are going in the other way. Okay. So before I said building a glacier will be a slow process. It takes 100,000 years or longer. For example, the last ice age on Earth ended around 20,000 years ago, 18,000 years ago. Actually ended around 12,000 years ago because it happened in hiccups. Nonetheless, that glaciation actually started almost 120,000 years ago. And it kept building, and the glacier came all the way to Long Island, and parts of Europe and southern hemisphere was also glaciated and so on. Why does it slow down? Some of you may be able to guess. Basically, as glacier builds and air cools, cold air is able to hold less moisture. So the amount of snowfall begins to decrease. For example, Antarctica is so cold, Arctic is so cold that most of the time it's just dry, cold air blowing. So the snowfall rate decreases, which means the glacier growth rate itself begins to decrease. So the glacier growth begins to get slower and slower. So the glacier builds slowly over a long time period. But what is happening now? We are actually increasing the temperature because of greenhouse effect, because of increasing greenhouse gases. Warmer temperatures begin to melt glaciers on Greenland and Arctic sea ice. Reduced glacier and reduced sea ice reduces the albedo or the reflectivity. It increases the amount of energy being absorbed by land and ocean, which makes the oceans and land even warmer and the atmosphere warmer. It melts more glaciers and the albedo decreases further and you keep warming. And this goes much faster because there is no limitation here. So the melting of glaciers can happen very abruptly. So the last ice age began to end because of orbital changes around 20,000 years ago. But in a couple of thousand years, almost all the glacier had disappeared. Okay, so that's the danger we are in now. We are in a melting phase, and Greenland melting is accelerating. Antarctica is a bit more complicated because it has ocean around it. If the ocean warms, it actually can snow more on some parts of Antarctica. And the Antarctic melting is a bit complicated because the land glacier that is flowing onto the ocean as shelf ice is melting because of this warmer ocean. When that shelf ice on the ocean melts, the glacier on land tends to slip towards the ocean and melt more. So there are some places in Antarctica where it's melting pretty fast and accelerating. Some parts of Antarctica, the ocean is actually, warm ocean is actually increasing the snowfall and is increasing the volume of ice. So Antarctica is complicated, but Greenland is basically heading towards increased melting. There are other details. For example, glacier is about 3 kilometers thick on Greenland. It melts at the top. Melting at the top creates a pond of water which has a much lower albedo than the ice. So the pond begins to get deeper and deeper because it absorbs more and more sun's energy. So it carves into the glacier and creates what are called moulins. There are waterfalls going into the glacier. And that goes sometimes all the way to the bottom. And water at the bottom begins to act as a lubricant and begins to slide the glacier towards the ocean if the slope is high. So there are lots of such details which we mostly have to understand by observing carefully. So in terms of what are the feedbacks, those are kind of, that's the most important feedback. Ice albedo feedback has been one of the most important feedbacks in the Earth system throughout its history. Of course, there are others. When we increase greenhouse gas, as I said before, atmospheric temperature goes out because of the trapping of long wave radiation. Warmer atmosphere holds more moisture. Moisture is a greenhouse gas. It traps more long wave radiation, makes the temperature warmer, and you have a feedback. Okay, so those are the kind of feedbacks you have. Geologically speaking, there are negative feedbacks. For example, a warmer atmosphere will lose more energy to the space because of what is called black body radiation. It's like the pot on the stove that is emitting more energy when it gets warmer, but it's the matter of time scales. Energy loss from the top of the atmosphere is much slower than the energy being trapped by CO2 increase. And warmer temperatures and rainfall and humidity also increase the weathering rates, which actually takes down the carbon dioxide. But that is also very, very, very slow time scale. So there are very fast time scale processes and very slow time scale processes. And the net effect will depend on what is the dominating feedback. The other good example is what happened in our own backyard here in India. As we know, Indian subcontinent was way south near Madagascar, slowly drifted across the equator. Around 70 million years ago, it started to cross the equator. Maybe about 30, 40 million years ago, it crashed into Asia, kept pushing forward northward. It's still doing that, subducting under the Asian plate. So Himalayas grew. They are still growing. And when you raise so much of the crust, you bring up a lot of the material, and the rising of the Himalayas created this monsoonal circulation which didn't exist before about 10 million years ago. So the rainfall increased. The rainfall began to wash away a lot of the material that is brought up by the mountain forming, and that weathering began to draw down carbon dioxide from the atmosphere. So this long-term cooling we have had since the time of the dinosaurs to the present is essentially related, at least according to one theory. There are other argued theories, to decrease the temperature, which has cooled by about 6 to 7 degrees in the last 50 million years. So we have global warming happening in this long-term cooling effect that has been happening because of the rising Himalayas and cooling because of increased drawdown of CO2. In fact, the rivers that come down from the Himalayas carry so much sediment load into the Bay of Bengal that land is sinking because of the weight. What does that mean? That means, relatively speaking, the sea level is rising in the Bay of Bengal. So Bangladesh and east coast of India actually are experiencing faster sea level rise because of the warming, plus this land sinking because of the river sediments. There are other examples like this. For whatever reason, you create an initial change, you warm the climate, you increase the temperature and precipitation and vegetation, which increase the so-called chemical weathering. Weathering removes carbon dioxide, which would oppose the initial warming. So this is kind of a negative feedback. This is another example of negative feedback.